Section 2.7 is on absolute value functions and graphs. The parent function of the absolute value function is f of x equals the absolute value of x. It is v-shaped and is symmetric about a vertical line called the axis of symmetry. It has a single maximum or minimum point, which is called the vertex. Here's a little table, a little chart from your textbook that shows some of this. So here's what it looks like in a table. Notice that for every x value, when that goes in between the absolute value bars, it ends up being positive. So for an input of -3, you get out a +3. Here's the function written as kind of function notation. Basically, the absolute value of x is equal to x when x is greater than or equal to 0, and the absolute value of x is equal to -x when x is less than 0. And here's what the graph looks like. In this case, the parent function is centered, the vertex is at the origin, and the axis of symmetry is the y-axis. So let's graph this function here. This one says f of x is equal to the absolute value of x, and then notice that outside of the function is a +3. And then we're asked, how is this graph different from the parent function? So I'm going to go ahead and make a simple table of values here and put in a few numbers. Maybe I'll use -4, -2, 0, 2, and 4. And when I put in -4, I get 7. When I put in -2, I get 5. Recall that those absolute value bars are making my x's positive. And then I get a 3, and a 5, and a 7. And you can see this nice symmetry in your y values. So let's go ahead and graph that. I think I'll start at the center here. 0, 3, -2, 5, -4, 7. And then the same thing over here, symmetric on this side. And there's what my graph looks like. Also, and so how is this different from the parent function? Recall that the parent function is centered here at the origin and goes up like this. So this is actually a vertical translation of 3 units. Translation of 3 units up. Here's another table chart from your textbook that talks about the parent function and the different transformations that you can do on it. As we saw in the previous example, we had a vertical translation, and because this plus k was outside of the function, that translated the parent function up k units. If it's a minus k, it's going to be translated down in a vertical direction, k units. A horizontal translation, so if you have minus h inside between the bars, x minus h between the bars, that's going to translate your parent function h units to the right. And if it's a plus h in the middle there, it's going to be translated h units to the left. Vertical stretch and compression is similar for functions that we saw in the last section. It's going to be a vertical stretch if a is greater than 1, and a vertical compression if a is a value between 0 and 1. And a reflection in the x-axis has a negative outside of the function, and a reflection in the y-axis has a negative inside the function. Let's take a look at this example. Which of the following is the graph of f of x equals the absolute value of x plus 3 minus 1? So we have this x plus 3 inside the function, inside the absolute value function. So that's going to be a translation left 3. And the minus 1 outside is going to be a vertical translation of down 1. So that means that the vertex that I'm going to be looking for is shifted 3 to the left, so that's a -3, and down 1, that's going to give me a -1. And looking at these graphs, the only one that has a vertex of -3, 1 is B. So B is the graph of that function. Notice that in the graph of the parent function, f of x equals the absolute value of x, the right side of the graph has a slope of 1. So for the graph of f of x equals a times the absolute value of x, a stretch or compression of the parent graph, the right side has a slope of a. So if we were looking at something that were like this side of the graph right here would have a slope of a. The graph of f of x equals -a times the absolute value of x is a reflection of f of x equals a times the absolute value of x in the x-axis. So it's going to look like this. Okay, and the right side has a slope of negative a. That's going to make it really easy to graph these if we know what the slope of one of those sides is going to be. So let's use that to do this one. So here we have to graph f of x equals negative 1/4 times the absolute value of x. So since we have a negative right here, it's going to be a reflection in the x-axis, so it's going to look something like that. Okay, since my a is equal to 1/4, the right side, so this side right here, is going to have a slope of 1/4, or because it's going down, it's going to have a slope of negative 1/4. And notice that there's nothing being added or subtracted to x between the bars, and there's nothing being added or subtracted to x outside the bars. So my vertex is going to be 0, 0. So I can go ahead and plot that point. And now I know this side, my right-hand side, is going to have a slope of negative 1. So I'll go down 1 and right 4, down 1 and right 4. And then the other side is going to be just a reflection across the y-axis. So down 1 and left 4, and down 1 and left 4. And there is my graph. I'm not drawing a real straight line there, but you get the idea. So when we combine translations, compressions, and stretches, we get a general form for the absolute value function. While the parent function is, you can do y or f of x. Y equals the absolute value of x. There can be changes, things added inside, outside, numbers out front. Here's the general form. Y equals a times the absolute value of x minus h plus k, where the stretch or compression factor is the absolute value of a, and the vertex is located at the point hk. The axis of symmetry is the line x equals h. So here we need to compare the function f of x equals negative 2 times the absolute value of x plus 2 plus 3 with the parent function. And that is, without graphing it, we need to state the vertex, the axis of symmetry, and any transformations of the parent function. So looking at this my value right here, that's going to be, or in between the bars, I'm going to have an x minus h, and outside here I'm going to have a k. So my h is equal to negative 2. Notice that the general form of the equation of the function is x minus h. This is x minus a negative 2. So my h is negative 2. My k is 3. So my vertex is going to be the point negative 2, 3. My axis of symmetry is x equals h. So that's x equals negative 2. And now let's talk about the transformations. Notice a is equal to negative 2. So this one is going to be, this means it's going to be reflected in the x-axis. Which means it's going to be going down like that. Okay, and it is vertically stretched. Oops. And the slope of this side right here is going to be a negative 2. My h, whoops, kind of sloppy. My h is equal to negative 2. That means that I'm going to have a horizontal translation. 2 units to the left. And my k is 3. And that means I'm going to have a vertical translation 3 units up. So this is really very handy. Without having to pull out your calculator or without having to make a table of values, I can graph this just from the information in the function. And our last example here asks us to write the equation of the function that is graphed below. So first thing I'm going to notice is, where is my vertex? And it appears to be at 2, 1. So that means that my h is going to be 2 and my k is going to be 1. I'm noticing that there's no reflection. Okay, so that means that a is going to be a positive number. A is greater than 0. It is vertically compressed. And it appears that the slope of this side is equal to 1/4. So I think that gives me enough information to write my equation here. So I have f of x equals 1/4 times the absolute value of x minus h, so x minus 2, plus k. So in this lesson, we took a look at absolute value functions and their graphs. We compared the parent function and the different translations that you can do, came up with the general form for the absolute value function, and discovered how to graph them and how to, from a graph, write the equation of the function.